Hello, everyone, and welcome to this short discussion where the article we are going to discuss here was suggested by basically by a comment in one of my previous discussion videos, which was on there are no particles, only fields. Now, the comment was given by, well, WBT, but that's, I think, is more known as the science hobbyist. So I will put an actual link to his YouTube channel as well. And so he recommended this article, which I was not aware of. So it was really a pleasure to read, which is called Anti-Photon, and that was authored by Lam. And Lam was like a really very important physicist working on quantum radiation and quantum mechanics of light matter interaction, stuff like that. And he has worked on the spontaneous emission problem. Is well known in kind of basic quantum theory, like for the so-called lamp shift associated to what we would call vacuum fluctuations of the electromagnetic field, and so on and so forth. And so in this 1995 paper that was published in Applied Physics B, essentially Lamb tries to make the case that he doesn't like the word photon, and he thinks that this is an unnecessary terminology and in fact misleading kind of piece of vocabulary that should be essentially not used when when physicists talk about light or light matter interaction. Um, so to be honest, the paper is fairly easy to read, at least for let's say the first like kind of 5 pages or so, and then there is a little bit more technicalities in there, but that's definitely not insurmountable. Um, so just to give a few highlights. So in fact, here, like it starts in the abstract by saying that there are very good substitute words for photons, and so you can talk about radiation, light, and you don't need to talk about photonics. You can talk simply about optics and quantum optics and so on. And I think the what he really doesn't like is this focus on light being made of particles, as if these particles had a very clear, if you will, identity that we could conceive of, etc. And there is quite a bit of history, and I think it's very nice because often we are not really versed in the history of it. There is some nice aspect related to the influence of Newton and how he influenced the teaching of optics in terms of particle based optics until the middle, almost the middle of the 19th century, and so on and so forth. Um, Now, there is some interesting parts that I'm going to go over that relates to Einstein. So when we talk about, for example, a particle-based model of light, one of the things that comes to mind is the photoelectric effect, and in particular Einstein's way of explaining the photoelectric effect, which was based on a quanta or quantum maybe of light that would interact in a particle-based fashion with, let's say, some electron or something, or with a metal, and then would give rise to an electron being kind of kicked out and so on. And one of the things that is noted here, that although Einstein gave some kind of qualitative insights that were, explaining what was going on in the photoelectric effect, from a quantitative perspective, that's actually not clear. Um, and in fact, one of the things, so that's some of the things mentioned here in 1905, and so here there is somewhere photoelectric current here, and and then the Einstein light quantum hypothesis fitted in very well with the above observations. However, Einstein was unable to calculate the rate of photoemission of an electron from either an atom or a metal surface, which apparently was to some extent worked out by Millikan. Um, but the thing is that quantitatively speaking, it seems that things were not easy to connect with the model of Einstein. Now, another thing that is quite interesting is that when people talk about photons, often they are going to mention lasers as being like almost just made up of a collection of these particles we imagine as being photons, and and then everything is focused on this apparently quantum phenomenon, which is the stimulated emission of radiation, because that's what kind of lasers stand for, right? So light amplified by stimulated emission of radiation. And so the quantum effect here appears to be stimulated emission, and there is hardly any focus on the spontaneous emission of light. And interestingly, actually, Lamb here discusses the fact that there is nothing mysterious about stimulated emission, and in fact, it can be done perfectly classically. And in fact, people who have done any form of semi-classical quantum kind of light matter interaction would see stuff like Rabi oscillations and so on, at least that would be forced by an oscillating field, etc., which basically are going to um, you know do not need any kind of photon in there. So the idea here is that there are plenty of things that people focus on that allegedly are due to photons, where Lamb says, no, actually here, I'm perfectly fine with a classical view. And his view, in fact, is that people should focus more on spontaneous emission, because that's actually the weird stuff going on, that things can spontaneously emit light. Um, Now, there are some aspects related to electronics, which and optics, kind of electro-optics kind of thing. Um, but then there is a part that is interesting here, and that is related to the work of Wenzel and Beck, and who apparently worked out the kind of the a quantum theory of the photoelectric effect, but that does not involve the word photon whatsoever. And they do actually get an actual rate that they can compare to experiments. And so that's quite interesting here, that basically there doesn't seem at least to be a need for this word photon to describe the photoelectric effect. It seems that it's possible to go or to bypass that alleged need. Um, Then there is quite a bit of uh, historical, um, you know, um, discussion on Lewis, and Lewis here. I take it as the Lewis model of kind of valence or covalent bonding and stuff like that, um, and perhaps even the octet rule and so on. So he was a physical chemist, so there is quite a lot of discussion there. And interestingly, the reason why Lamb talks about Lewis is because he was the one to introduce the word photon. And the interesting bit here is there that the word photon was introduced by Lewis in 1926 in some letters he sent to Nature, and the word photon was actually used as a word to talk about a particle that would be somehow bound or attached to an atom, and somehow that would help in the perhaps in the binding process, in the covalent bonding process, but also in the radiation process. And apparently, there is some. I haven't read that paper, so maybe this will be a next read in one of our discussions. Specifically denied that it was the light quantum of Planck, Einstein, and Bohr. So he didn't have in mind a light quanta, or light quantum, sorry. Instead, he had something completely different, which was about radiation, but it was not related to light, and it was some sort of actual real particle that could be bound to an atom. So that's kind of interesting. And so, although these aspects of the photon has completely, vanished, and in fact, I was never personally aware of this one. It turns out that the word was catchy enough to be taken on board quite fast, and basically within few decades, everybody just talks about the word photon. So that's kind of interesting. Now, the Lamb actually also mentioned that, of course, because there is photons, we need also to have phonons. So people who are into condensed matter physics, they may appreciate that people want to express everything in terms of particles, and so there's going to be phonon scattering with electrons or with some defects and stuff like that. And again, that's interesting to determine to what extent this is necessary. Um, Here, for example, Lamb mentioned that he was able in 1939 to provide a theory of the Mörs-Bauer effect without any use of the word phonon. So again, there is this interesting aspect which I really like to emphasize on this channel, which is on the when it's possible to actually bypass the alleged necessity of some concepts, of some techniques, and so on. And often there is a case where these alleged necessities can be completely ignored and basically, used or dealt with by with somebody else, with something else. Um, I think, as far as these historical parts are concerned, I think I'm mostly done. Um, the only part that happens that is a bit more technical here is is here. So it's in the last 3 pages. Um, so people who are familiar with the mathematics, they can read it. The bottom line here is that he explained very quickly that what happens is that you can discretize, discretize, or yeah, you can expand, let's say, the expression of your field onto a basis. And this basis is associated to what are called normal modes. And these normal modes are going to depend essentially on the boundary conditions of your problem. And that's what you call the hard material conditions of your experiments. That can be a waveguide, that can be an actual microwave kind of box, so like a superconducting kind of cavity, whatever that is. So it can be plenty of things. It can be freely, radiating in the universe with nothing kind of as obstacle. So it can be kind of plenty of things. But in fact, where this is going is that the fact that we talk about modes, first of all, does not identify these modes uniquely because they are contingent on the, in fact, outside of the box. Um, and one of the things mentioned as well elsewhere, so that's where he discusses the radiation field with one mode. He does concede that if you've got one mode, and this mode is, let's say, unambiguous and so on, then you could maybe talk about photons. And in his mind, at least, that the only place where that kind of makes sense to talk about photons is when you've got a well-identified mode and the radiation field is only with this mode. However, he does emphasize that although you can create, if you want, a sort of superposition of kind of waves, so it's a single mode, and you can have a sort of um, linear superposition of number of photons in each mode. That's fair enough. You can do that. Um, but then what he wants to emphasize is that there are really problems when it comes to photons that have no parallel with electrons and other typical particles of matter. And one of them is that photons, for example, cannot be localized in any meaningful manner. So these are things also related to special relativity. There is no way to have a sort of local beable at all when it comes to photons. Um, and they indeed don't behave at all like particles, and whether you try to describe them with a wave function or not. So that's kind of the idea. Then there is something else which has to do with when people talk about the so-called one photon state. That's something very kind of basic that people learn when they do some introduction to quantum field theory. And it turns out that actually even that doesn't necessarily work very well. And the reason why is because essentially that's a sort of limiting regime, so something that happens at infinite time or very large time or something, which is kind of approximate. Um, but then you don't have a one photon state. You have actually a superposition of one photon states. So a superposition of one photon states, which involve actually an infinite number of tensor products of kets, and then where for each of these kind of states, you only have one mode being occupied and all the rest not being occupied. Um, so that's not a one photon state according to him, because there is much more than one mode that can be occupied. So according to him, that's not really uh, good to talk about photon in that case. And essentially the point here is that that's what he says, is that at at the end of it, you've got normal modes. These normal modes really correspond to whatever constraint they are in the field outside of it, and you just need to take that seriously and talk about normal modes and so on, instead of talking of some particles that basically are going to change identity or how they should be conceived of every single time you change the setup, the experimental setup. Um, and basically that's kind of it here. Um, I think he also has a bit of thing against Bohr, for example. Well, basically, he says that discussing concepts like photons and stuff like that has led a bit people astray, in the sense that when you actually deal with the calculations, actually this photon stuff is not useful. You need to actually look at the modes, you do whatever, use perturbation theory on these modes and so on, but without ever, in fact, mentioning the word photon. In fact, some people do recognize that if you have to use the word photon, then you tend to be a bit, you get into trouble, like especially if you start talking about virtual photons, for example. So at the end of it, essentially, Lamb is very much anti-photon. He thinks people should use other terms to talk about optics. And one of the things that he mentions as well, and that's actually quite striking, is that when you take the classical limit of quantum field theory or quantum radiation theory, then you get actually Maxwell's equation. And Maxwell's equation, they don't comprise particles. Um, and that's actually contrary to what happens if you take, let's say, the classical limit of some electron problem, right? Electron interacting with another electron. If you take the classical limit of it, you still have an electron interacting with another electron via, for example, Newtonian mechanics or something. And so you see that it's quite different. The classical limit is not the same. The classical limit somehow does not preserve the the photon aspect of it, which is kind of strange, and perhaps indicating that this is at least it can be considered superfluous, and perhaps misleading to continue using it as much as we do, let's say, these days. So if you've got any comments or questions, any further kind of advice on things to read and communicate about, by all means, do let me know in the comment section. And otherwise, see you in the next video.